Thank you all for joining us today. I'm Erin Bebuck, the Director of Development for Engineering and Physics. On this webinar, you'll hear talks from 4 faculty members. They'll last 8 to 10 minutes, and after that, you'll meet one of our physics PhD students who will tell you about his research and the impact of philanthropy on his work. Next, we'll have an audience Q&A. If you have questions for our presenters, please use the Q&A function, which you can find at the bottom of your screen, to drop those in at any time during the presentations, and they'll be answered at the end in our panel session. Closed captioning is available for this event. You can turn it off or on using the CC button at the bottom of your screen. And if you have any technical issues, please use the chat to reach me during the webinar. I'd like to introduce our host today, our VP for Research, Jill Pipher. Professor Pipher is the Elisha Benjamin Andrews Professor of Mathematics, and she has served as our VP for Research since July 2017. She's an advocate for the role of research and mathematics in society, and she came to an interest in quantum through her research in cryptography. Jill?
Thank you, Erin, and thank you all for joining us today. I'm really excited to have this opportunity to showcase some of the cutting-edge quantum science research that's taking place at Brown. And I'd like to begin by describing the larger context in which the research that you're about to hear is situated, both at Brown and elsewhere. Quantum science and engineering is an incredibly dynamic and exciting field. In its modern incarnation, it brings together experts in biology, chemistry, engineering, computer science, information science, mathematics, medicine, and physics. Quantum science has become a field of urgent priority for governments, for major businesses, as the effort to build a quantum computer advances. A quantum computer would have completely different architecture from a classical computer in order to take advantage of the physical principles that govern subatomic particles, and in order to compute in ways that our phones and our laptops and even supercomputers cannot. Quantum science is an even bigger enterprise encompassing this gigantic, ambitious project. It involves the creation of a whole variety of new technologies, new communication systems, and all harnessing the physics of electrons and particles. Quantum mechanics and the modern study of particles and electrons began in the early 19th century with the work of Max Planck, Albert Einstein, Erwin Schrödinger. Early quantum technologies gave us the transistor, which was in fact the fundamental component of our classical computer. Today, there are a huge number of technologies that come from quantum science, including nuclear magnetic resonance imaging, MRIs, lasers, high-energy light sources, solar cells, electron microscopes. The technology for GPS systems uses Einstein's theory of relativity, and the quantum science makes possible atomic clocks whose precision is required for accurate GPS location. Quantum science research across the world and at Brown aims to understand and control individual quantum states and systems, and to develop a theory of quantum information, what a quantum computer will do better, what it won't. And this research has resulted in and will continue to give us innovations in computation, in digital communication, and sensing applications, and many more. At Brown, we have researchers working in many areas of quantum science: quantum theory, quantum systems, sensing, materials. These researchers are responding to the National Institute of Standards and Technology challenge in post-quantum cryptography. They are building the next generation of quantum cameras. They're creating new imaging capability. They're predicting and harnessing molecular behavior at the atomic scale to reach that grand challenge of building a quantum computer. Today, you'll hear about a few of these exciting research developments in quantum science at Brown. And now I'd like to introduce my co-hosts, Gang Xiao and Larry Larson. Gang Xiao is an experimental condensed matter physicist focusing on nanoscale physics and devices. He's the chair of Brown's physics department and is a professor of physics and engineering. Larry Larson is the inaugural Sorensen Family Dean of Brown's School of Engineering. Dean Larson's research is focused on the development of new semiconductor devices and circuit techniques for faster wireless communications. Dr. Xiao will introduce our speakers, after which Dr. Larson will moderate the Q&A. Thank you.
Thank you, Jill, for this wonderful introduction. I'd like to welcome all for joining us today. I'm very pleased to introduce our first speaker, Brenda Robinstein. She is a Brown alumna. She received her PhD degree from Columbia University in chemical physics in year 2013. Brenda is developing theoretical electronic structure method so that she can conduct material designs using theory. Her research interest involves molecular and quantum computation and also computational biophysics. Brenda?
Thank you for the gracious introduction, Zhang, and in particular, that's a very gracious introduction indeed. So today I'm really thrilled as a Brown alumna, actually class of 2007, if 2007's out there, to tell you about the really exciting and phenomenal quantum science research we're doing here at Brown today. In particular, I will tell you about some of the research that my group has been doing in order to create quantum algorithms that can predict the design of materials from the bottom up. So one such material that I show here is bilayer tungsten ditelluride chromium triiodide, and I'll talk about those materials in a second. So a lot of this story, like many stories in quantum physics and in quantum science, really starts with Richard Feynman. As many of you know, Richard Feynman won the Nobel Prize for his brilliant findings in quantum electrodynamics back in the 1960s. And he's one of the most, how shall I say, eccentric and phenomenal communicators of physics of our time. And so Richard Feynman said many different things over the years. One such thing that he said is that physics is like sex. You can do it, and it creates new things potentially, but that's not why we do it. And also profound things like, I would hate to die twice because it would be really boring. But in all seriousness, Feynman said some extremely profound things that really started the quantum science revolution roughly 60 years ago. In 1959, at the APS meeting, he gave a talk that's called There's Plenty of Room at the Bottom. And during that talk, he outlined the fact that what he thought chemists to be doing and physicists to be doing right now really didn't exploit all of the many different possibilities for the way that we could build materials up from the bottom, atom by atom, one at a time. Indeed, according to Feynman, what he tried to think about is what would happen if we could arrange atoms one by one the way we want them. And that was a great thought. Like many things that Feynman thought, it was absolutely true, and it set forth the whole field of nanotechnology. But the thing about that thought, as much as he was correct that there was plenty of room at the bottom, and there continues to be plenty of room at the bottom, there's actually an astronomical amount of room at the bottom. And that might sound like a great opportunity, but it's actually a huge problem for quantum engineers like me. So according to many estimates, there are greater than 10 to the 60 or 10 to the 80 atoms in the universe. And if you imagine trying to make a material, if you wanted to say, how do you make this material from all of those different atoms, that would be an incredibly challenging task. Right? You have to think about 10 to the 80 possible combinations of different things. That's a huge number of possible combinations. And so this is a huge problem. Now, you might think that's kind of a Q combinatorics problem that some quantum physicists like me have to think about, but this is really a very practical problem. If you want to design the materials tomorrow to satisfy our insatiable hunger for new materials that have better energy densities, that have shorter discharge times, you have to be able to predict the materials that are going to get you to those different properties. If you want to make better batteries, you need to predict those shorter discharge times. If you want to make better photovoltaics, you have to be able to predict predict the materials that are actually going to be able to harness sunlight more efficiently than others. And so the old way that people used to do this is through experimentation. And I kind of like to joke. It's not so much of a joke in chemistry departments. The old way was, you get a lot of graduate students and they try materials and they try materials and they try it again. And that still kind of works, but the way that we like to think about things today is through the view of computer-aided materials design. What we want to be able to do is to be able to predict properties before you ever set foot in the lab, so that when you do, you only have one graduate student or one person working hard on that project instead of dozens and dozens just trying things and trying things. Even more recently, there have been machine learning techniques that have been developed to try to directly predict which materials will have which properties. And so this is a successful program. I'll get back to this program at the end of my talk. But there are materials that really challenge this. And in some sense, quantum materials inherently challenge this paradigm of just being able to predict things. So in quantum materials, they often have things that we call correlated electrons. These are electrons where if these are systems where if one electron moves, other electrons really know about it. They're really affected by it. And so for materials like transition metal oxides, these are things that make superconductors. Things like 2D materials, which I'll get back to in a second, and lanthanides and actinides, that electron dance is very complicated. And so we can't just compute these things, the way that we would always do for many other things in our classical environment. And so these materials create sort of a trouble in paradise. And so what you might say, if you know any chemistry, if you took my course, Chem 330, 33, or 220 back then, you might know that we should be able to solve the Schrödinger equation and solve all of these different problems. H psi equals E psi, we're done. But the problem is that for these materials, the Schrödinger equation is kind of like a cookbook that doesn't tell you how to put the ingredients together. So here are the ingredients. Go make your blondies. It's very hard to figure out how to get this wave function. And so people like me try to create new means of finding that wave function. So just to give you some insight into why you can't just solve the Schrödinger equation, for these materials in which there's a very strong electron dance where they're really correlated, we have to actually count all the states of electrons. And you can imagine if you have a huge material, this becomes really, really hard to do really quickly. So if you're lucky and you have one orbital and you have 2 electrons, you can have 1 state. If you have 2 electrons and 2 orbitals, now you have 4 states. If you have 2 electrons and 3 orbitals, now you have 9 states. And you see how this is going. If you have a material with thousands of orbitals, you're going to have an exponential number of states, and you just can't do this counting. Or at least I'm not doing it. Maybe you're doing it, but I'm not doing that counting. And so what my group has been doing is creating a variety of what we call quantum Monte Carlo methods. These are methods that use stochastic sampling, meaning they use random numbers to determine the properties of different quantum materials. These are highly accurate methods, but what their benefit is that they are very, very, very fast. So some of you who are in the data science fields or maybe in statistics may be familiar with Monte Carlo methods for classical systems, for classical problems. And you may know that Monte Carlo methods are usually used to calculate things like integrals and areas very quickly. So for example, if you want to calculate the area of a circle, what you could do is you can throw a whole bunch of darts at that circle and keep throwing. And you can throw those darts randomly. And all you have to do to find the area of that circle is count how many dots are in the circle versus in the larger square in this case. So that's a quick way of calculating the area of a circle without knowing its properties. Similarly, what we do in my group is we calculate the properties of wave functions. We calculate wave functions by throwing similar kinds of darts and just keep throwing them until we can obtain all of the different characteristics of a given wave function. So you might ask, okay, that's great, you can do that, and you'd be right. For about 40 years, people thought of these kinds of methods, but they didn't really do anything. Maybe they calculated hydrogen, which I guess some people will say is important, but not as important as other things. But what my group has done is really made these methods into practical devices for predicting quantum materials. And so one application that we've looked at recently is what we call 2D materials. This is actually a strong point at Brown. We have a number of researchers working on these materials. What these materials are single atom thick layers that you can stack on top of each other. Graphene is a great example of this. I think we'll hear more about this, graphene, later. What makes them phenomenal is the fact that now you can put them together in different arrangements. You can stack them, you can stretch them, you can crinkle them, you can do lots of different things to them. And if you do that, you're going to get materials that have entirely different properties. And so in this sense, these are kind of like material Legos. You can stack them together in different ways and get the kind of structure that you imagine, the structure of your dreams. And so in particular, what my group has been looking at, let's say, over the past year, are different types of bilayer 2D material systems that have magnetism. So one such example of that is a material called Chromium Triiodide. So it has chromiums and it has iodines. And it was actually one of the first 2D materials discovered that was magnetic, inherently magnetic. Actually, people debated whether you can have literally atom layer thick magnets, but in fact we can. And this material was really the first discovered that had these properties. Now, for many years, people weren't actually sure what the moment was on the chromiums in these materials. So exactly what was the magnetism in these different chromiums. And so what my group has done over the past year or so is actually use the methods that I was talking about to practically predict exactly what the properties of these and other 2D materials are. So for example, in the case of chromium triiodide, we were able to actually map out very explicitly through all of that sampling where the electrons are, what their spins are probabilistically throughout that material. And we were able to see that actually chromium has a much higher moment, it has much stronger magnetism than anybody ever actually thought before. What we were also able to show is that for this material, its magnetism is strongly coupled to its geometry and its vibrations. If you stretch it, you get completely different magnetism than if not. And if you turn it on as a magnet or off, you're going to get completely different vibrations between those two different cases. And so this is a really, really interesting finding for those in the field. But most of all, what it shows us is that, yes, in fact, we can do computer-aided materials design. We can develop quantum algorithms that are highly accurate, that can now predict exactly what materials we should be using in our different devices and exploring in the lab. So this is great, but I would honestly call it maybe the first paradigm, maybe some of the first thoughts that Feynman had way back then. Being able to predict and then design different materials is sort of ground, stage one in the quantum revolution. But what I'll leave you with a thought that we're currently working on right now is maybe there's another stage beyond this. Instead of trying to find the materials that do what you want, why don't you let the materials evolve to the properties that you need? So instead of finding, let them find themselves. And so this is a new thing, a new hot thing that we're trying to work on at Brown here today. And I'll leave it for next time to tell you how that's going. But this is another exciting paradigm. So with that, I would like to acknowledge all of the important people that made this happen. Let me just say that I have a group that constantly makes me look and feel good. I'm not as good as they are. I'd like to thank in particular Dan Staros, who's a third-year graduate student here. He's a NASA fellow who's done much of this 2D material work. Annette Lopez, who's picking up with some of that. And I'd also like to thank the Department of Energy and the Brown Center for Computation and Visualization, who continually both support our work through funding and through many computer hours. Thank you for your attention. Happy to take questions later.
Thank you, Brenda. The next speaker is Professor Brent Marston from Physics Department. He is the Assistant Director of Brown Theoretical Physics Center, Professor of Physics. Brent studies non-equilibrium statistical physics of climate and oceans, and with the understanding of climate change. He also conducts research in many-body quantum systems, such as quantum spin liquid, quantum magnetism, superconductivity, and also actinides. Right.
Thank you, Gong, for that kind introduction. I want to talk to you today about some work that we're doing to try to answer the question of whether quantum computers can be useful for simulating the climate. And the theme for this talk is drawn from a quote by Robert Heinlein: "Climate is what we expect, but weather is what we get." So the idea behind this quote is that climate is the statistics of weather, And so the question we're asking is whether we can use quantum computers to directly find the statistics of the weather system. So simulating the climate is of crucial importance, especially as the climate is changing, but it's very difficult for traditional computers to do. And this is a picture of the supercomputer center in Wyoming that's run by the National Center for Atmospheric Research. The reason it's in Wyoming is that electricity is cheap there, and the air is cool and dry, so it can be used for evaporative cooling of the computers. So we want to see if we can do a better job using quantum computers. This is a kind of high-risk, high-reward research. We're not sure where it's going to lead. This is a movie that I'm going to show you of water vapor in Earth's atmosphere last month in October. And I want you to pay attention to the west coast of the United States. The bluish color means that there's a lot of water vapor. And when you see this in motion, you'll notice that there are some bands of moisture that are reaching California finally. And in fact, around October 26, a large rainstorm, an atmospheric river, as these bodies of moisture are called, put out the horrible fires that had been burning in Northern California since the summertime. But understanding whether these atmospheric rivers will change as the climate changes is a delicate matter and something that's a challenge for current climate models. This is a view of one of these atmospheric rivers going clear across the Pacific Ocean, reaching British Columbia, where it often goes. In fact, right now, British Columbia is having some flooding due to an atmospheric river event. Notice that California, this is several years ago, is dry, and there's smoke coming off the coast from fires that were burning in Sonoma County that killed over 50 people. So understanding how these atmospheric rivers will change is one of many questions that we want to try to address. The atmosphere isn't the only fluid part of the Earth that's complex. The oceans also have a lot of rich structure in the ocean currents. This is now 2005. We see the warm current that's bringing in warm water into the Gulf of Mexico that will power Hurricane Katrina that destroyed parts of New Orleans. All of this structure is also difficult to capture with traditional supercomputers. So now I'd like to turn to ordinary water waves. This is a view of a tank of water in which light is coming through the tank so we can see ripples, the crests and troughs of the water waves. And the water waves are going to be generated by a plate in oscillation at the bottom and impinging on a screen where there are two holes. And when this is set into motion, you'll see that there's an interference pattern with strong waves going out in one direction and quiescent places in other directions. So this interference pattern is a well-known property of classical waves, but it also occurs for the quantum world. What we're seeing here is light hitting two slits and passing on to a camera that can detect individual photons of light. And we see the same sort of interference pattern, but now this flickering is the individual particles of light reaching the screen. So this is an experiment we do at the physics department at Brown, because we have a super sensitive camera that can detect individual particles of light. And now we're turning down the intensity of light so that the photons, these particles of light, are arriving at a much lower rate. And you can see that they seem completely random. There's just no way to predict where any one photon will arrive. This is the randomness that's inherent in quantum mechanics. The fact that quantum mechanics is a statistical theory, it can predict the likelihood that a photon will arrive at some point in on the screen, but not where any one particular photon will arrive. And this will be made clear when we instruct the computer in a few moments to record a time exposure of these photons So now the computer is continuing to leave those photons where they arrive at the screen, and we see that the interference pattern, it reappears once the exposure goes long enough, showing this, again, the statistical properties of quantum mechanics. So we want to know if the mathematics of quantum mechanics can be put to use to understand the statistics of the Earth climate system. So we've been working with some simple models to begin with, because quantum computers right now have modest power, but these models have been inspired by the climate system. This is the Lorentz attractor that I'm about to show you that was discovered by Ed Lorentz, and it illustrates the phenomena of chaos. And like weather, this particular system is sensitive to where we start the simulation. So what we're going to see are two trajectories started at slightly different initial positions, and there's going to be a blue trajectory here and then a yellow trajectory. And you can see that very quickly these two trajectories diverge. This is the reason why we can't predict the weather far in advance. But no matter where we start, we always flow to the same statistical pattern. And if we take a time exposure, just as we did with the photons, we see that there is a reliable pattern that evolves. This is like our climate. So what we've done is to accumulate these statistics over a long period of time, as I've done here in this movie, but compare this to a quantum algorithm running on a classical computer here, and the results are identical. Now, this gives us some confidence that this approach will work, but the quantum algorithm running on the classical computer is very slow. It takes hours to run. And what we want to know is whether a quantum computer can speed this up. So we've teamed up with a company called IonQ that's developing a high-quality quantum computer. They just went public and raised several $1 billion because their technology seems to be quite good. And we expect that quantum computers like this can allow us to make an exponential speed up of our simulations. So perhaps we could achieve the same result in seconds instead of hours. This is a blow up of their device where they trap ions in laser beams in a line and then are able to carry out quantum computations using those ions. So this is research that's being carried out by two Brown undergraduates, Ding Wei and Ethan Swagel, and a master's student, Yidong Zhou, as well as with Professor Brenda Robinstein, who you just heard from. So for high-risk, high-reward type research, working with undergraduates and master's students is a good fit because, unlike PhD students, they don't have to have a final result at the end of their studies. As long as they're learning, then this is a positive thing. So we can afford to take more risks with them than we would with a PhD student. So we're developing these capabilities, and as the quantum computers themselves become more capable, we'll then apply this approach to more and more realistic models of the climate, models that involve the fluid motion of the atmosphere and the oceans, and see how far we can go with it. So thank you very much for your attention, and I'd be happy to take any questions at the end during our panel discussion.
Thank you, Brett. Our next speaker is Professor Vesna Mitrovic. She is a professor of physics and engineering. She received her PhD degree from Northwestern University, major in condensed matter physics. Vesna does research in condensed matter experimental physics. She uses nuclear magnetic resonance, very similar to MRI used in hospital, to probe quantum materials, such as unconventional superconductors, quantum magnets, and also other quantum solids, particularly in nanoparticles or quantum or topological phases of matter. Vesna?
Thank you. So, hello.
I'm going to be talking about research that we are undertaking in my group and with my colleagues here at Brown to really advance technology that would eventually enable us to create like universal, very powerful quantum computer. And at this stage, the research I'll be talking about is a little bit more theoretical, and that's the reason that Brenda explained, even though I'm an experimentalist, experiments are very costly, so we really want to make sure that theoretically we know what we're doing before we actually go and do these impossible and very expensive experiments. Eventually, that's the goal. So as you heard before, our life, modern life, would not be possible without quantum mechanics. It's full of examples where quantum phenomena are kind of used to make MRI imaging, lasers, and my favorite of all, resonant tunneling diode. This is actually a device that turns on our cell phones. Can you imagine your life without your smartphone today? And all the telecommunication is actually based on use of this very simple quantum device. So what is this new quantum technology that we actually are working on is that it would be nice to take these little devices and then combine them to create the true quantum machine that uses the full power of quantum mechanics to give us these really amazing machines. And one of such would be to allow us to have completely secure telecommunications and, of course, a quantum computer, which is a dream for all of us, physicists, chemists, and scientists. So a quantum computer would allow us to really tackle complex problems that we can't even imagine solving today on classical computer, and also would allow us to do efficient fractionalization of prime numbers that eventually is necessary to provide secure communication, for example. So our credit cards numbers would never be stolen again. So what is it that gives quantum system this advantage over a quantum computer? What is it that makes it so powerful? Well, the basic building block of a quantum computer is a qubit, quantum bit, and unlike a classical bit, a quantum bit over there, that is psi, the wave function that you saw in Brenda's talk, it's a superposition of zeros and ones. And this phase there that we have can be anything. So in principle, you could encode an infinite amount of information into this qubit. So why is it that we don't have a quantum computer when it's so simple? Well, the problem comes with inherent stochastic nature of quantum mechanics, what my colleague just showed you, Brent Marston, in his talk, and that is the fact that the measurement is random. So if I was to read out the information that it's written in that qubit, the result of my measurement could only be 0 or 1. I would never learn about the phase in a single measurement, okay? But that said, there's another property that makes a quantum so powerful, and that is coherence or entanglement. So what I have here in this picture, imagine this qubit, this red arrow here, that it's entangled with another qubit, which is the white arrow in this other circle. And if I do something, if they're entangled, okay, or coherently coupled to use a technical language, if I do something to this red arrow, instantaneously there will be a change in the state of the white arrow. Instantaneously, regardless of how far spatially they are apart. As a matter of fact, recently there's been an experiment where 2 photons of light were entangled and sent out between Cambridge and Oxford in Britain, universities, right? So 40 plus kilometers apart, and when one was measured or changed, the state of the other instantaneously actually changed. So this is extremely powerful. The problem is, it's easy to do it with photons for telecommunication, but if we want to make a quantum computer, we need a material, we need a device, something. And so we really, theoretically, I guess, we know how to write that for a pair of photons, but how to figure out the complex entanglement when we have these correlated electrons interacting system is really impossible. This is my cartoon of what we think. Actually, we really don't have an idea of how this entanglement looks, and these green lines are just all the possible patterns of entanglement between these electrons that interact, okay? So why do we actually want to know this entanglement in material? This is really a main goal of my research that I'm leading, is to try to figure out how to measure entanglement in materials. Well, if we knew that, we could construct a topological quantum computer. So this is the ultimate quantum computer that we would like to have. And the reason is actually quite simple. In principle, this is a theory, why this works. You can initialize this computer. You see, you have these like little white and blue dots. So these are kind of qubits. The bits, just 0 and 1s. But you see these lines, they kind of tell you about that phase, the superposition, that quantum mechanical thing that we can't measure. And then, in order to do the calculation, you braid, just like the strings. You see on that picture, my hand braiding the strings, it changes the wave properties, right, on the surface of the water, kind of, okay? So here, you take these particles for different paths, and they accumulate different phase. If you have noise, impurity, which you always have, no material is perfect, it only affects one of these paths, not the whole thing. And so it doesn't really matter. And then you can read it out and do whatever with this information. And so this is what we want to have. This ideal machine would allow us to actually do this universal quantum computing without really having to perform error corrections to any complicated extent. But the real problem here is that, well, we don't know what this entanglement in materials. We don't know the nature of this topological order, meaning how to braid these things. We don't even know whether such particles exist. And so this is really what is kind of a goal of my research, to try to figure out what is it, this topological order. And once we know that, can we actually build the methods to encode and read out information without preserving all this quantum information that is contained in this machine? And so in order to do that, well, there are actually proposals, theoretical, that what allows you to produce these little lines there is special particles that are called fractional excitations, and they're called anyons. And let me explain what they are. So the first step, if you want to ever make this topological computer, is to find such particles. So there are two types of particles in nature that we teach our students in the textbooks, and that is bosons and fermions. And let me explain what the fermion is. Boson. You basically take a particle and you take it for a loop, okay, around another boson, and when it goes around a full circle, you see its wave function, its kind of quantum signature stays the same, remains the same. And then we have fermions that if I take a fermion around another fermion for a full loop, it actually picks up a minus sign that you can see there. So you have to circle it twice to return to what you started with. And then in 2 dimensions, we have a very special world where there are these particles that are called anyons. You can see there, they pick up an arbitrary phase. So they can be anything when you take an anyon around another one. So it allows you to actually create a very complex topology of these paths for braiding and do the computation. The problem is, again, there's no classical probe that we have at our disposal in physics or engineering labs that would actually provide an evidence for existence of such particles. And so this is really the goal of our research, that a holy grail is quest for anyons at this point, okay? And this is kind of what we are working on at this point, kind of theoretically, that there are really 3 directions. One is noise spectroscopy, resistively detected NMR, and interferometry. The noise spectroscopy is, the current is carried by discreteness, by electrons, by charge, and it produces telegraphic noise, actually. Just like a telegraph when you have these discrete carriers of charge. So these anyons they are very complex objects. And so if you record the current carrying by them, they actually show that the current is carried by a fraction of a charge of an electron, okay? As if somebody chopped the electron in pieces. The challenge with that is that you have to do the experiments at very low temperature, and you also have to make sure that electronics is super low noise, that you can eliminate all outside sources of noise, and it's been really very, very hard to do. And then with my colleague Brent Marston that you just heard, we have actually developed a technique in order to kind of test that there are these topological states on the surface of metals, and also propose of how to manipulate, read out eventually the information into such a topological states. And then the last is interferometry. And you just heard about interference actually from Brad's talk. That picture on the top is exactly identical classical waves that Brad explained, an interference pattern that comes from basically a phase difference at the point where they meet. And so anyons, because they have that arbitrary phase depending on what path they take, they should actually produce the same thing. As a matter of fact, I'm showing you the real data that was just published about a couple of months ago, where there is a device, and those little red dots are real, like supposedly anyons. It's an interference device where you actually look at the interference pattern between these supposed fractional excitation anyons. And all these lines here mean different phase combinations. Now, so the problem is solved, right? We have a technique, it's published. Please, I want to draw your attention to the temperature at which this was carried out, 22 millikelvin. This is 22, it's very close to absolute zero. So these experiments are extremely challenging. And this is why we don't have the machine. It's really hard to imagine that we'd have your computer somewhere at these temperatures that you have to maintain this. And so there is actually another set of materials that are called quantum spin liquids, where we expect to have that at about 100 times higher temperature, 2 Kelvin, 4 Kelvin. That's easy to do, okay? But the problem is that these materials are electrical insulators, so we can't do this kind of experiment. And so what my colleague Dima Feldman proposed is actually to do not charge interferometry, but the heat. Every material carries energy, carries heat. Heat is also extremely difficult to measure in absolute sense, absolute amount of heat that is carried to your device. So the really beautiful proposal is to actually look at two devices with a different geometry. And that difference between the two now would give you a smoking gun evidence for the existence of these anyons, basically in any material, regardless of whether it carries a charge or it doesn't. So it really opens a new avenue if you could ever implement these experiments to probing this topological order. And I'm just going to stop with kind of a big picture for our goals, is to identify this topological order, then use it to perform these to sense things that we were never able to see before, and ultimately, design these powerful computers and be able to read out quantum information. So, thank you.
Thank you, Vesna. As you can see at Brown, we are developing all kinds of quantum devices and materials for quantum computer. I want to introduce our final faculty speaker, Jacob Rosenstein. He is a associate professor of engineering in the School of Engineering at Brown. Jacob received his PhD degrees from Columbia University in 2012. He's a Brown alumna. And so a quantum computer offers many alternatives to a classical computer, but there are also other alternative methods to classical computer. So Jacob has been doing a lot of exciting projects in this area. Jacob.
Thank you. I'm so happy to be part of this. Thank you all. So it's true that I'm going to be a little bit of an outlier. So far, the great talks that you've been hearing have been all about quantum science. And I think that the work that we do is generally more in the classical space. However, it sort of implicitly includes plenty of quantum science, and maybe tends to give a little bit of the flavor of the places that things can go after technology really gets going. Where's the clicker? So my background is more in electronics and information science and sensors and things like that. But what I like to do is to take that technology and maybe turn it upside down, or to put it in an unusual place, or to stretch it to fit some of these great new materials and new scientific applications that we're hearing about. A trend that I'm sure that you all know and that you all use and that you all rely on has been the 50 years or even more of Moore's law. And Moore's law has been wonderful for all of technology. And as you, I'm sure, are aware, it's the trend that as semiconductor technology has gotten better, what that has meant is that transistors get smaller. And as they get smaller, they inherently get cheaper because you can put more of them on the same device. They tend to get faster because they're physically smaller and the electrons don't have to move as far. Because they're smaller, they also end up being lower power. And because they're smaller, you can end up putting more of them on the same device and adding more capabilities. So all of this is just a win-win-win for everything. and it has driven all of microelectronics and so much of society recently. So this is all wonderful, and I hope it continues. But a complement to this is maybe thinking about the way that all of this growth in electronics and this growth in semiconductors is able also to drive new applications and is able to sort of bring in advances in other materials and bring in advances in other fields and lend itself to other fields. For example, in the way that as devices get smaller, all of a sudden they get portable. All of a sudden they can be incorporated into devices that maybe traditionally would have been a little bit more passive, would have been a little bit more isolated from the kinds of networking and connectivity that we all love. So for example, I think it's fair to call it a trend now that a lot of biotech companies are now hiring chip designers and becoming semiconductor companies in a way. And this is the kind of thing people sometimes give it the nickname of more than Moore, where we can use the semiconductor technology as a platform to incorporate and to interface with other technologies. So one of the things that we're doing in the lab, which I think has a nice, good synergy with a lot of the quantum science that we're hearing about, is that together with Pradeep Guduru in the School of Engineering, we are aspiring to make the world's fastest thermal microscope, and to use that to study the way that materials heat up and fail and fracture when they rub against each other or come into contact with each other at very small scales and at very short time scales. And so in order to do this, we've designed a custom chip that will receive the photons from a sensor. The sensor is designed to receive photons from infrared light when materials heat up, but unfortunately this material has to work at very low temperatures, as we're hearing from a lot of the really interesting quantum applications. And so we need to be designing the electronics to also work at the same temperatures. Now, in some ways, this is an advantage. I can only imagine how much you could overclock your GPU if it were surrounded by liquid nitrogen. But in a lot of ways, it introduces new challenges, and it has us maybe thinking about the ways that we're going to need to stretch and twist the traditional silicon chips in order to let them live in the environments that are needed to support other sensors and other materials. So I talked a little bit about how biotech is maybe absorbing some silicon technology into its own work. So one of the other things that we're like to think about is maybe bringing silicon technology into more biology applications. And so for example, we've been working on a project where we are trying to bring arrays of sensors on silicon chips into the environment, into the field, to collect and grow and study new types of bacteria. It's a known fact within microbiology that most bacteria won't grow in the lab because we don't know what conditions it needs. And so what we are trying to do is to make microscale and integrated platforms to bring out into the field to study the bacteria in their environment where they live, and maybe use that to discover new species, new antibiotics, things like that. So we also want to help all the people who want to use advanced semiconductors to study biology. As everything gets smaller, as everything gets more sensitive, eventually we reach, in some ways, the quantum limit of biology, which are single biomolecules. So for example, all of the DNA sequencing platforms that are growing and growing eventually reach a level where they would like to sequence single molecules of DNA. And that necessarily means dealing with a lot of statistical issues, dealing with a lot of more unpredictable, faster moving, weaker signals that come from single molecules. And so we want to be bringing the most advanced silicon technology to to that application to reduce the noise, to speed up the measurements, to improve the quality of all the sequencing. And I think that in the same way that Moore's law has brought down the cost and increased our imagination for what we can do with semiconductors, the way that DNA sequencing has been improving over a couple of decades has really changed the way that people imagine the applications and the spaces where sequencing can be applied. One of those places is maybe the way that people are now starting to be able to realize the sort of long-standing thought of DNA as an information-carrying molecule. So I think if you spend your life doing sequencing, you don't have to stretch to really just start thinking of DNA as just carrying information. And so there's really interesting thought experiments and real applications that are coming from thinking about DNA not as just carrying biological information, but maybe as carrying other types of data as well. So if you could imagine, and people have been doing demonstrations like this, of writing abstract data, of writing video files and spreadsheets and whatever into DNA that has no biological meaning, but that you could put in a freezer or put in a capsule at the North Pole for 1,000 years and expect to get it with a good expectation to get your data back at the end. And this is really interesting, for one, because it maybe pushes the boundaries of what we think of as sort of the realm of electronics, but maybe pushing it into the chemical space. It makes us think about biology in a different way, and maybe it helps us think about how the information that we process maybe ought to be tailored to the materials that we are going to be using it with. And so in thinking about chemicals and thinking about molecules as information, at Brown we've also had a good collaboration going for a few years, and this is also together with Brenda Robinstein, who you heard from, where we would like to be thinking about all other sorts of molecules as also capable of representing information. It's not a stretch to think about all the ways that cells don't just contain DNA, they have all kinds of other molecules that are that carry information. And so, for example, if we can make mixtures of molecules that maybe stand in for all the different metabolites that are processed in cells, we can also think of those as carrying information. We can also do this with all other sorts of molecules, and in the same way that the combinatorial space of all kinds of electron structures grows and grows exponentially, so does the space of possible chemical structures. And if we can place ourselves in that space, maybe in the same way, in some ways that people search for new types of drugs, we can use that space to represent some information. And I would love to talk more about this a little later. A current and ongoing project that I think kind of brings together some of these ideas also is that we would love to think about chemicals and molecules as carrying information, and we would love to think about living things as processing that information. So if there's a way to think about having chemical data that turns into other chemicals, then you can think about that as an algorithm that is computing on that data. And so although it's going to be a little bit of a science fiction type of flavor to it, we are aspiring to be building systems in a current project where we are going to be growing bacteria on semiconductor chips. And what we would like to do is to maybe think of those bacteria as a little living coprocessor, where maybe we can have some electronics that offload a little bit of computation into the cells. The cells do what they have evolved to do, but maybe we can capture some of that predictable behavior as a computing device. And this is not to say that this is going to overtake our iPhones or that you'll have one of these in your pockets, but I think it opens up new spaces that are perfect for research and perfect for exploration. That about sums it up, but I've been happy to share this all with you, and I think that these types of spaces where we interact between traditional electronics, new materials, new applications is a great place for research, a great place for training, a great place for industry to interact with things that happen at the university. And thank you all for listening. So I'd like to welcome Dean Larry Larson now for the next phase of the talk.
Thank you, Jacob. We'll move the podium to the center. So, is that good? Okay. So I hope that the talks that we've seen this afternoon give you some hint of the excitement that is going on at Brown in the field of quantum science, and the revolutionary impacts that this research will have on computing global warming, drug discovery, cryptography, and many other fields in the future. Now, in order for Brown to be a world leader in this field, we have to recruit the brightest people on the planet to come to Brown, and we have to give them amazing equipment for them to do their experimental work. So speaking of recruiting the most brilliant people in the world to come to Brown, I'd like to introduce our next speaker, a graduate student, a PhD student in the Department of Physics, James Zhang. James is the inaugural awardee of the John Chi and Christine Gong Graduate Fellowship in Experimental Condensed Matter Physics. And James is going to talk to us about the importance of philanthropy in supporting these important efforts. James.
Well, thank you, Larry. As you heard, I was the recipient of the first John Chi and Christine Gong Fellowship in Condensed Matter Physics. Having this fellowship allowed me to think big. It allows me to push forward research projects that would significantly advance our understanding of the quantum science. At the same time, it also, the outcome of this research could enable a wave of technological revolution that has widespread real-world applications. For example, one of my research aims to look for nanobillion particles, actually anyons, as Professor Mitrowicz just mentioned, using fractional quantum Hall effect in graphene. These particles, when their position exchange, their quantum mechanical property changes in a very unique way that allows us to encode information. And information encoded this way will not be lost due to noises unless we deliberately unexchange them. This behavior is at the heart of a proposed scheme for quantum computation. Up to now, there has been little progress in realizing these particles in 2D materials. The fellowship offered me the golden opportunity to step beyond fundamental research and pushed towards the direction of one day realizing quantum computation using these nanobillion anyons. Large gifts like my fellowship can support graduate students or even postdocs and professors, allowing us to focus on our research without worrying about how to support ourselves. Well, I cannot speak for postdocs or professors, but as a second-year PhD student, when I received my fellowship, I can say that it has increased my productivity in the lab for about 50%. Imagine what another 2 or 3 graduate students can do in their 50% of time. Smaller gifts can help too. In a research lab, we have so many consumables, pipettes, chem wipes, or even PPEs such as masks and gloves. They may not seem to be very expensive, but adding them together also yields a considerable amount of expenses. We really appreciate your help in creating a safer and more comfortable working environment for us. Not just that, gifts to the Physics Chair Fund and Engineering Annual Fund can provide supplies to student labs, support undergraduate students working on summer research projects, and help faculties to explore new directions in their research too. We hope you've enjoyed this presentation, and I invite you to support all these amazing works through gifts to Brown Physics and Engineering. Our Director of Development, Erin, will share giving links where you can donate directly. She will also share her contact information in case you'd like to consider a transformative gift. Please stay with us as our faculty panelists set up for an audience Q&A and submit your questions through the web Q&A function.
We've set up the panelists to handle Q&A, and it's my great honor to moderate this part of the session this afternoon, and some great questions have already come in via chat. So I'm just going to read them off one by one to the panelists, and we'll have a bit of a discussion. So Brad, this is a question from Teddy Parker. Which quantum algorithm is the basis of your climate simulation? I'm not aware of any algorithms for NISQ computers that are known to give an exponential speed up over classical computers for this kind of fluid modeling.
Right, so first we use the Fokker-Planck equation to transform the equations of motion, the nonlinear classical equations of motion, into a linear equation, which is a lot like the Schrodinger equation. And then we use quantum phase estimation to find the zero mode, the eigenvector with zero eigenvalue, which represents the statistical steady state. So that's where we get the exponential speed up. So it's a different approach than some other approaches that have been used to look at differential equations, because it focuses right away on the statistics of the problem, and therefore it's able to take full advantage of the quantum speed up that's available in a quantum computer.
Thank you, Brad. The next question is from Marty Stalen, and it's one I think for the whole panel. Do quantum computers harm the environment? Any thoughts on environmental impacts of this work? Don't be shy.
Well, maybe I'll say something. Yeah. So that I showed that giant supercomputer in Wyoming, which is powered partly by electricity from coal-powered plants, which Wyoming has lots of coal. So climate scientists have asked themselves, are we harming the environment just by carrying out our computations? And so you could envision that a quantum computer would be much more efficient and thereby might reduce those kinds of costs from the traditional computation.
We would still have to cool down, so nothing is for free. Definitely better than a classical computer, but nothing is for free. Yeah.
Thank you. So another great question has come in. I've read that quantum computing is like, contained nuclear fusion, always 30 years in the future. What are your estimates of the time that a useful, widely available quantum computer will be available?
Sounds like 30 years.
It's always difficult to project exactly when these kind of technologies will take their form. But we already have quantum computers that are online. The argument is just how truly quantum they are. But they are already solving interesting problems. So they're solving interesting statistical problems. And in my field, in quantum chemistry, we actually can model small molecules using quantum computers at this point to very, very high accuracies. And so even though these are initial demonstrations, they're getting there. Things are progressing. Every few weeks there's a new development of larger processors or a better algorithm that these computers can solve. So it might be 30 years, could be 20 years, but we're making steady progress.
The problem right now is that very few qubits are coherently coupled, so we don't really use the full power of quantum computing. So the absolute record is 8 qubits that a controllable that was done in Santa Barbara. Coherently controlled. But there is, as Brenda said, the whole set of problems where that's enough actually to offer really big advantage over even a supercomputer.
Mm-hmm. Isn't there also a problem with the time that they remain coherent, which is strictly limited?
That limits how many,
yeah.
Yes, exactly, how many gates you can imply, how many manipulations, so.
Great question. Let's see. Dr. Robinstein, have you looked at super/ultra capacitor applications as part of your research into new 2D materials?
Sure, really good question. So we're a little down the line than assembling the different materials, but yes, the capacitors are one of the key applications for the kinds of materials that we're trying to explore. So a lot of our work is trying to understand fundamentally what their properties are, but these are absolutely the class of materials that will be used for capacitors in the future.
Another question from an anonymous attendee is, what fraction of this work is classified? More broadly, nationally, and is any of the work that we're doing here at Brown classified? by the US government?
So Jacob and I have worked for DARPA and DoD, and none of our work is classified. We're very happy to say that. A lot of our work sometimes informs some of that work, but all of our work is unclassified.
And none of my work has ever been classified.
Same here. It's really a basic science that absolutely nothing is classified so far. I mean, that's...
Yeah, likewise. Even working sometimes with the Defense Department, the kinds of things that they're interested to partner with us on are generally the parts that they wish that everybody in the world understood better, not the parts that they're going to keep secret.
One question that's come in from Neil Veloso: what effect could quantum computing have on distributed ledgers, such as blockchain? Interesting question. I'm not a blockchain expert. Any ideas? Okay.
I don't know. I mean, it sounds like it would completely change the way that we do cryptography.
Yes.
Yes,
So
it can certainly-
it would open up the blockchain and require different algorithms in there.
I don't think we're there yet for those applications, but we're getting there.
Very good. Here's a rather deep question that's come in from David Simons. I have a very basic entanglement question. When two electrons are entangled, separated, and then measured, they are found to collapse the same way. Instead of considering this as a spooky action at a distance, why couldn't it be interpreted as both electrons have been preloaded, quote unquote, to collapse the same way, no matter when or where they are? So that's a basic quantum physics.
Brad, you want to? They don't collapse the same way. That's the whole point.
They don't collapse the same way.
Yeah, so one collapse is, say you do a measurement and you collapse and you get
Right.
an output.
Good point.
While you actually did that measurement, the other one changed, right, instantaneously.
In the other direction. Yeah. Or some other
Arbitrary.
direction.
And
Yes.
so what actually you can do is I can set my detector whichever way I want. So Brad can set his, he's dealing with the other electron, right? And then I would have to tell him the result of my measurement, and then he puts what he found, and then we can actually work it backwards. What was the entanglement? So I don't know if that answers the question in a very complicated way, but the
Right.
point is that they're, how do I say this? We don't find the same result. It depends how he orients his detector, how I orient mine.
That's great. Peter Scott asks a question first for the whole group. For all, where do you see the overlap/room for collaboration with the computer scientists, specifically the computer science department at Brown, in the near term, in this general effort?
I think we're really excited for that collaboration. One thing I think in the field is because of some of the questions that were asked earlier. A lot of computer scientists ask, are quantum computers going to be here? Are they really going to do the hard problems? Is our beyond Moore computing also going to do these really hard problems that we can do in silico? And silicon's hard to beat, so sometimes it can be challenging to convince computer scientists at this point. But more and more are coming on board and starting to think about these problems. And I certainly value computer scientists working in the algorithm space. I think a lot of times we need help, with things like Brad's work, developing those algorithms. And so I'm looking forward to more opportunities to work with computer scientists down the line.
I'd add that quantum algorithms are still in their infancy, and so there's a lot of space for finding new ones and also improving the efficiency of existing ones. So computer scientists could certainly help out in that direction. And then there's an idea of having hybrid computing, where you have a classical computer and a quantum computer working together, each doing what it does best. And so the understanding of computer scientists would be crucial for such a device.
So another question from Peter Scott for Professor Robinstein. Is there anything particularly interesting with respect to the core computer science concepts? For example, programming languages, compilers, et cetera, that's being used for computer-aided material design?
Absolutely. A lot of the A lot of the calculations that we do for quantum materials are extremely expensive, I'll put it that way. If you want an accurate description of what's happening to the electrons, what's the magnetism, what's the topology, we have to do intensive calculations. And so myself and collaborators, we spend a lot of time thinking about how do we get things to run very smoothly on a variety of different processors. And in my group, we actually use the biggest machines in the world, the leadership computing facilities at DOE, which have a variety of different processors working on these problems to get these calculations to run. And so the question for us is not only algorithmically, how do we bring down time? Maybe that is actually mathematically, that is maybe using quantum computers, but also on classical computers, how do we bring down that time? How do we better use resources? How do we better run our calculations to make this work possible?
Thank you. So at this point in time, I think we've answered all of the questions that have come in from the audience. One question that maybe I'd like to throw out to the panel, and Brad, you mentioned that one startup company just went public with a quantum computer of some kind, unclear what. Are there other things that people are doing in the entrepreneurial space around quantum computing and quantum sensing that are very interesting right now that we should be watching, or like who's kind of leading the field from an industry perspective in the work that's going on?
There are still many different possible approaches to quantum computing, and it's not clear which approach, if any, of the current ones is the best. But IBM and Google and IonQ that I mentioned are three of the contenders. And so the IonQ computer uses trapped ions, which is quite different from the approach that IBM is using, which is based on superconductivity and Josephson junctions. So it's still a very fluid area, and there's a lot of development, and things will shake out, I'm sure. But it's an exciting time for the development of quantum technologies.
One of the biggest bottlenecks for IBM, and I know from our collaborators, was really the amplifiers, RF, so radio frequency, at low temperature, so making the electronics that Jacob mentioned work at, and just lack of really people trained in, this is very recent trend, and so we are, I think from hardware point of view, really missing a lot. Industry needs a lot of people that are educated. They know how to use cryogenics, these low temperature electronics. That's just, commercial instruments all made for room temperature. And this has been the last 6 years of IBM, for what I know, in a qubit computer, is really, they have the entire groups dedicated to just having, RF preamplifiers to be able to address the qubits and read out, work out efficiently, this problem of measurement and stuff, errors that are associated with that. Something so simple, and it's the same technology that we use for communications, except, you have to cool it down. And you would think this is such a simple problem, but, so.
Yeah.
Really.
One more question has come in. This is an interesting question. How would a photonic computer change any of the work that you're doing? Would it be a competitor, I guess, potentially to a quantum computer?
Well, a lot of photonic computers are quantum computers.
Yeah.
And so it's one class of the many architectures that Brad was alluding to before. One of the advantages with photonics is light is fast. It's very fast. And so you could run a number of different algorithms very, very quickly. We also, I think, Brad and Vesna were alluding to, we understand a lot about the entanglement properties and how to deal with them with photons. And so that's another advantage of that architecture. But it's one of many architectures.
So related to that, a question has come in from Michael Atisha, who is a Brown PhD physics, class of 06. How do the panelists view the relative importance of increasing qubit lifetime versus developing error correction techniques? Recognize this may depend on the type of qubit technology, but curious as to general thoughts on each type of approach to avoid information loss? Question mark. Great question.
Right, so there's many different trade-offs that have to be made in building a quantum computer. And so the stability of qubits versus how rapidly the computations themselves can be performed is one classic trade-off. And there are different ways of quantifying how good quantum computers are. And I think there's not any one single measure that is able to capture all of these different aspects. But certainly the coherence time and the lifetime of qubits is an important criteria.
So all those things have to be done at the same time. So we have to improve coherence, but then if you don't have enough coherence, then you can't even possibly really think about error correction. So they're a little bit intertwined.
That's the first step, I would say. Right? How many? But then, the error correction could be quite complicated, right? Mm-hmm. So you might need more gates to correct that. So coherence is definitely a first step, and then it goes from there.
Just returning a little bit to the previous question about different technologies, Microsoft has been putting in a lot of money to topological quantum computing along the lines of some of the ideas that Vesna discussed. So that's a really ambitious effort to try to protect qubits from decoherence. But it's so ambitious that they really haven't taken the first step yet. So
we are at the point where we don't even have a qubit, basically, topological qubit. We don't know, right? We're at that point, but it's great, if we have it, it would be a real leap.
Yeah, it's great that they're willing to.
This is why we're doing it.
Okay. Any other questions from the audience? I see one perhaps sort of final question was, are there any plans for future update sessions on this topic? So I see that this has been a very popular session today, and we still have a very robust attendance out there. So I really appreciate everyone hanging in and coming to this exciting session today. And we'll do more sessions as we make progress in the field.
If we have time, I would like to just kind of add another thing that we never had time
yes,
to
please,
discuss.
Vesna, go ahead.
And something that me and Brad worked or thought about it. It's a computation is one practical thing that I think most industries, we're interested in having a quantum computer. That's just kind of would be fantastic. But the quantum sensing technology or these devices that we could develop along the way, if we had these topological materials, it's really, for us as a scientist, really important. For example, there's more and more talk than, we could basically test everything that it's tested in particle accelerator. Instead of building these gazillion billion-dollar facilities, we could actually design tabletop experiments to probe really the foundation of physics. And something that goes under the name of beyond standard model, right? We all know how the world supposedly started. We could actually test whether this is really that way in the lab with these quantum sensors. And there are, again, we're at infancy, right? But it's really amazing what this technology could allow us to do, right?
Thank you, Vesna. That's great. One other question just came in, and Jill, I don't know if you would like to say something. There's a question, is the Brown Computer Science Department working on quantum-resistant encryption? NIST is standardizing this now. And Jill, Vice President Pipher, who started off the session today, is a world expert in this exact area. So Jill, I hope you don't mind if I ask you to come up and answer that question.
No, thank you very much. Actually, there were three of us in the mathematics department that invented a public key crypto system in the mid-1990s, which turns out to be resistant to the speed-ups afforded by quantum computers. So we're all really rooting for the existence of a quantum computer. But one subtle point is that everything that's encrypted today, your financial information, banks, governments, is encrypted using technologies that can all be broken when a quantum computer exists. And so whether that's 20 years from now or 30 years from now, there's information that we want to stay encrypted and secret for longer than that. And so that's why there is some actual urgency with, with quantum technologies and communication. Thanks, Larry.
Okay, so let's see here now. Another question has come in. A question for Professor Robinstein. It is great to see the connection of bio to semiconductors. Any work related to information protection for information protection? For example, a building system to protect, compensate for thermal degradation? Question mark.
I think that's
Information.
Okay.
I think that's Jacob.
That's from
Jacob.
here.
Yeah, it said Rubenstein. Yeah, sorry. You're right.
Sure. I mean, I think if you imagine encoding your data into some chemical form, you would certainly want to be thinking about degradation. I think the main protection against that at the moment is making things very cold. But certainly, I guess, well, some of the work that Brenda and I have done has been thinking about writing data into other molecules that maybe could be more chemically stable at higher temperatures for longer amounts of time. I think that's all. It's all. You know, if some of the quantum science is early, I think that this is even earlier. But certainly lots of people are starting to think about things like that.
Okay. Well, I think that's the last question for today. And first of all, I want to thank the panelists for their amazing talks, for all the great questions that came in. This is a really exciting field. As you can see, we have to bring the brightest people in the world to come to Brown to be leaders in this field. And we had 4 of the brightest people in the world here this afternoon giving us these great talks. So I hope this is just the start of many future events like this. And at this point, I'll say goodbye and thanks to everyone out in cyberspace for attending this afternoon. I hope you had a great time. Thank you.